talk about the data. Last time we talked about challenges, and now we would like to address the first challenge, so the data quality. And for that, we will be talking about data collection and data pre-processing steps. What are the problems we can have when we collect our data? So the first of them we can name as sampling rate. Sampling rate is nothing more than the frequency, how often you collect your data point. For example, if you have a temperature sensor and you can collect every second, or every 2 seconds, or every millisecond. But for some variables, for example, concentration, when you need a very advanced techniques, very advanced equipment to measure them, for example, liquid chromatography or gas chromatography, in this case you cannot measure the concentration very often and on very specific times. In this case, it might be the fact that if we consider a timeline, and here we have our process variables, process values, we can measure the temperature because it's completely automated. You can measure temperature very precise and up to, for example, every millisecond to get a measurement. But as I already mentioned, if you're talking about advanced methods, that also expensive because you need a person who will take the sample, bring it to the device, to the machine, and then probably you need additional substances, additional solutions to carry out the analysis, and so on and so forth. And at some point you have the, for example, concentration measurements that you have, for example, every hour or every 2 hours. That's not optimal for our case, and why it's a problem, because if you consider building a model, you have a certain set of input features. So you have your model, you have your soft sensor, you have input, and you have output. And the input every time should be the same. For example, if it's 2 features, 2 elements, then every single time you would like to run the model, you need both of them. And that's a problem if they have different sampling rates. That's why there are so-called hard to measure and easy to measure process variables. In this case, temperature is easy to measure and the concentration would be hard to measure. What are the options how we can deal with that? First option is to use so-called downsampling of easy to measure data. In this case, we say, let's take these values and find appropriate values of easy to measure variables. And I think, as you already can imagine, there is a problem, information loss, because in this case all of them will get lost. It's not the optimal technique, but sometimes it's exactly a technique, the only one you can use. Other options would be upscale or the upsampling. Basically, when you try to have these measures and you try to interpolate hard to measure variables, it's not that easy because in this case you need a model and it might be the problem as well. Other technique you can apply for this problem is so-called finite impulse filter, impulse response. It's based on filters and it's an advanced technique. It has different models you can, or different filters you can apply with different parameters. It's another challenge from that. So basically how to find the parameters of the filter, how to find the proper one. But in this case, applying the finite impulse response, we can get the, we can synchronize our measurements. Another problem we have with data, especially in the process industries, is missing data. It's not hard to imagine. Some sensors can stop working at some point. You might want to exclude them from the model, but again, because you have a fixed amount of features for the model, you cannot do that, and that's why you need somehow to deal with that. So you can imagine, for example, a table of your features. Let's say they are already sampled properly. For example, 1, 2, 3, 4. And at some points, for some of them, we do not have any value. For example, the communication with the sensor did not work well. Or for example, we have some calibration problem with the sensor. There might be software, hardware problems, whatever. But the fact is that some of the rows, they have missing values. How we can solve this problem? So the first solution, the most unsophisticated one, is like to delete rows with missing values. So indeed, it's very simple. You just remove the lines. In this case, it's exactly the problem with as we had with downsampling. So we lose some information and we cannot restore it further. That's why we would like to apply one of the so-called imputation technique, when we try to fill in missing values. For sure it's harder, and we need to apply different methods how we can do this, but it's worth it in most cases. The easiest approach would be if you have, for example, time series. So you have, for example, concentration measurement over the time, and you have some variables, some values, and for example, here you don't have any. And the same here. Nothing here, nothing here. What can we do? So basically we say we take the previous one and place it here. Or we can take the next one. So that's why they called forward fill and back fill. Or you can take this one and place the value from the next parameter here. But it's mostly for the time series you can apply this. For other types of data, you can apply other techniques. And they are indeed based on models. So you need to build a model behind your data, behind your existing data, and using this model, you would like to, let's put a time series. Forward fill and back fill. And and behind we need like real model. But there are some, let's say, statistical models. So basically you try to find the correlation between the parameters you have between them and apply this correlation on the data with missing values. And for that, two of the methods are most popular. First of them is so-called maximum likelihood. So where you apply model-based interpolation. For that, because you assume that your data follow a certain distribution, you need to select a distribution and the parameters first. And the second technique is called expectation maximization. It's similar to the maximum likelihood, but it's an iterative method. So basically you find the parameters for the distribution you assume, then you fit the parameters, then you fill in the value, and you start over. And you do it more times or until you do not have any changes in your parameters. And then you say, yeah, I don't have any changes anymore, and that's why I assume it's already converged and no more improvements you can expect further. The third problem in our data, it's outliers. Outliers if you think about them in statistical way, you can think about the data where you have like a distribution where you have a lot of points, and some of them, very rare points, they're somewhere outside our range where we have the most points. And that's exactly the first technique how you can define outliers. It's so-called free sigma. You have your your average value, and you have free sigma right and free sigma left. And then you say everything within this range, it's more than 99% of all the data. Then you say it's our normal data. But if the data point lies outside of this range, then it will be defined, it will be recognized as an outlier. And in this case, you can, for example, apply the imputation technique, or you can just remove this point from your data set. Another technique, like the first one, another is called Hampfel identifier. Where instead of the average value and the sigmas, you just have another statistics. There are also other multivariate techniques. So because you assume that you have a distribution here, and if you assume you have 2 dimensions, then it will look like something that. But it's not the true if you have, for example, data like this, because those are not outliers. It's like another scale for this dimension. And for such data, there are so-called multivariate techniques. So now you can think, okay, I can apply these techniques on my data. That's great. And then train the model. That's right, you must do this. But also you need to apply these techniques on data that are coming from the plant in real time. Because the same way you can have, for example, if you have your data from real time and concentration measurements, then you can have, for example, here, it's okay. But at some point you don't have any data at all. But you have other features, for example, temperature, that have those data. And to run the model for this time, you need for sure also this one. The next time, as soon as we have the data pre-processed and our training data, test data, validation data sets pre-processed, as well as implemented our pre-processing steps in our pipeline for the real-time data, we can think about modeling.